satellite S is moving with constant speed v relative to the Earth along a fixed circular orbit as shown in the figure. The satellite is sending radio signals of frequency f0. A station located at point P on the Earth detect these radio signals. The variation of the frequency f detected signals as the satellite moves from A to B is best represented by. The satellite is moving along the circular path from A to B. And the station P is located at this place. Velocity of satellite at point A is in this direction. Therefore, we can consider the distance from satellite to P station is decreasing from this point to this point. When the distance is decreasing, the station P could observe a greater frequency than actual value. Actual value is f0. From this point to this point, there is a greater apparent frequency. And after passing this point, the distance between satellite and station is increasing. Therefore, the apparent frequency is less than real value. Then we can get from this point to this point, there is a high frequency, and after passing this point, there is a low frequency. Then answer should be 4. Two cars are moving along a road at a constant speed as shown in the figure. The driver of A is sounding the horn from horn of his car of frequency f0 continuously. Initially, the car B is moving faster than A. Suddenly, B slows down and stops. A continues to move at the same speed and passes B, which is stopped. The graph that best represented the variation of frequency of F sound heard by driver B with time. For the initial situation, A is the source, wave is emitting in this direction, and B is the receiver. Both are moving in same direction. And they have given initially the car B is moving faster than A. It means the gap between two cars is increasing with time. Therefore, apparent frequency should be a frequency less than real frequency, a less than value. Then B is stopping. Therefore, after stopping, A is coming towards the B. Therefore, the gap between two cars is decreasing. then we can observe a greater frequency, a frequency greater than actual value. After passing B, the gap between two cars increasing with time. Therefore, again, we can observe a frequency less than actual frequency. But for this situation, B is at rest. The increasement of gap per second is a greater value than initial situation. Therefore, final situation, final apparent frequency should be less than this initial value. Therefore, graph should be like this. Then we can get answer is 5. A source of sound is moving to the right with the speed of sound. Which of the following figures correctly shown the propagation of wave front? A source of sound is moving to the right with the speed of sound. We know that there are three main conditions. First one is source is moving, but speed of source is less than velocity of wave in medium. It should be like this. Source is moving in this direction. Second situation, source is moving with the velocity of wave. It should be like this. For this condition, velocity of source is less than velocity of wave. For this condition, velocity of source is equal to velocity of wave. In third condition, if the velocity of source is greater than velocity of wave, it should be like a cone. Source is moving at a greater speed than velocity of wave. Now they have given a source of sound is moving to the right with the speed of sound. Therefore, answer should be like this. This is answer 2. A child seen a scene. Here's the sound from stationary whistle located in the direction where he is facing as shown in figure. The minimum and maximum frequencies of sound heard by him are 1314 and 1326 Hz respectively. If the speed of sound in air 330 and air remains still, what is the wavelength of the sound emitted from the whistle? We have to find the wavelength of sound emitted by whistle. For the maximum apparent frequency, the velocity of receiver should be towards the source. Gap between source and receiver is decreasing. Therefore, we can observe a maximum frequency, and this maximum frequency could be heard at the lowest point of the moving path of string. Because of we can observe a maximum velocity of the receiver at the lowest point. I will consider velocity of receiver is v. Then we can write F dash equals velocity of wave related to receiver divided by velocity of wave related to source multiplied by real frequency. They have given maximum frequency 1326. In getting velocity of wave related to receiver, wave is moving in this direction. We have to stop the receiver. To stop the receiver, we have to give opposite velocity to the receiver, and we have to do same thing for the wave. Then we can get velocity of wave is 330 plus v divided by velocity of wave related to source is 330. There is no any change because of source is not moving. Multiplied by real frequency. I will substitute real frequency as f equals, we know that v equals f lambda, then f equals v over lambda. We have to find the wavelength. Then I will substitute v over lambda. Velocity of sound is 330 divided by lambda. We can cancel out 330 and we can get that it is the first equation. 330 plus v divided by lambda. Then I will consider the minimum apparent frequency. When getting minimum apparent frequency, it should, value is 1314. It should be equal to velocity of wave relative to receiver. We can observe a minimum frequency when receiver is moving in opposite direction. Therefore, we have to give opposite velocity to receiver. We have to do same thing for the wave. And there are opposite velocities for the wave. Therefore, we have to subtract 330 minus v divided by lambda. Lambda is not changing. Now there are two equations. We can solve to find the value of v. I will divide it. We can cancel out lambda and lambda. Then I will use the cross multiplication. 1326 into 330 minus 1326v equals to 1314 into 330 plus 1314v. Then I will get all v terms to one side. And we can subtract 6 minus 4, 2, 2 minus 1, 1, 12v equals to, we have to add v values, 6 plus 4, 12 into 330 equals to 6 plus 4, 10, 1 remaining, 2 plus 1, 3 plus 1, 4, 3 plus 3, 6, 1 plus 1, 2, 2640 v. Now we can cancel out 1, 0, divide by 4, 6, divide by remaining 2, 24 divided by 4, 6, 66, divide by 4, 3. Then we can get 3 divided by 2, 1.5 meters per second. It is the v value, velocity. Now we can substitute to the first equation or second equation to get the lambda value. I will use the first equation. Then 1326 equals 330 plus V value is 1.5 divided by lambda. Then lambda equals 331.5 divided by 1326. We can get the answer 0.25 meters. It is 25 centimeters. Then answer is 3. Number 5. An ambulance which emits a sound of frequency F0 from its siren is traveling with constant velocity V0 along a straight road. A car starting from rest is moving behind the ambulance in the same direction, and velocity time graph of the car shown in the figure. The car approaches the velocity V0 of the ambulance at t0 time. The variation of the frequency F of the siren sound heard by a passenger in car with time is best represented by velocity of ambulance is given as V0, and we can consider the velocity time graph of car. For this situation, velocity of car is increasing, but velocity of car is less than velocity of ambulance. Therefore, we can hear the frequency of apparent frequency of wave is increasing, but it is less than F0 value, less than real frequency. Then for the second situation, velocity of car is constant and velocity of ambulance also constant. Therefore, apparent frequency is a constant value, but velocity of car is less than velocity of ambulance. Therefore, the apparent frequency is less than real frequency. And then again car accelerates like this. Its final velocity is V0. Therefore, the car can hear actual frequency at the final situation. Then answer should be 3. During the tsunami warning, a stationary siren emits sound wave of frequency 1600 Hz, while a wind is blowing at uniform speed 60 meters per second from the shore towards the land. A person hearing the sound of siren is driven his car away from the shore towards the land at 30 meters per second. If the wind blows at direction of motion of car and if the speed of sound in still air 320, frequency of sound of siren heard by the driver is. Now, source is at rest. Velocity of wave is 340 in still air, but there is an airflow in this direction, same direction. Therefore, we have to add velocity of air to the velocity of wave, 370. Now, receiver is moving. No, speed of air is given as 60. Then 340 plus 60, 400. Velocity of receiver is 30. Now we can use F dash equals velocity of wave relative to receiver divided by velocity of wave related to source multiplied by 100%. When getting velocity of wave related to receiver, we have to give an opposite velocity to the receiver and we have to do same thing for the wave. Then we have to subtract velocities. 400 minus 30, 370. divided by velocity of wave relative to source. Source is at rest. Therefore, we can substitute actual velocity. It is 400 multiplied by in this value we have to use S naught, real frequency. Real frequency is 1600. Then we can simplify it. 4 into 7, 28, 2 remaining, 4 into 3, 12 plus 2, 14. 1480 Hertz. Then answer should be 2. A whistle emitting a sound of frequency F moves along a circumference of circle of radius r at constant angular velocity omega. V is the velocity of sound in air. The highest frequency of the sound heard by the listener who is at rest outside the circle is. Now, source is moving in a circle and receiver is at outside the circle. If he is near to the circle, he can receive a maximum frequency at a point like this, moving towards the receiver. Source is moving towards the receiver. If he is, if the distance between circle and distance between center of circle and point of observer is a greater value than radius, we can consider that he can observe a maximum frequency at this point. For both situations, velocity of source is r omega. We know that V equals r omega, tangential speed, tangential velocity. Now, we have to consider the wave in this direction. Velocity of wave is given as V. Now, apparent frequency equals to velocity of wave related to receiver. Receiver is at rest, then V. There is no a change of velocity because of he can observe real velocity of wave because of he is at rest. Then for the second situation, velocity of wave related to source. Source is moving in this direction. We have to give opposite velocity r omega to the source and wave. Then V minus r omega multiplied by real frequency F naught. Then we can get answer is 1. Number 8, a whistle that is used to train a dog produce a frequency 22 kilohertz, which is more than the threshold of hearing of human. The trainer of dog wants to make sure that the whistle is working, while the trainer stands by the side of a long straight road. He has to tend to blow this whistle from a car moving along the same road, the required speed of the car and direction of motion, the car of the trainer, so that to hear the whistle at the threshold of hearing 20 kilohertz. They have given speed of sound in air is 340 meters per second. The actual frequency, real frequency is 22 kilohertz. It is greater than threshold value. We can hear frequencies between 20 hertz and 20 kilohertz. Therefore, apparent frequency should be threshold value. It means 20 kilohertz. Therefore, there is a decreasement of frequency due to the relative motion. It means the car should move away from the receiver. We have to find the value of velocity. Now wave is like this. Velocity of wave 340. Then we can get actual real frequency equals velocity of wave relative to receiver divided by velocity of wave relative to source multiplied by real frequency. When getting velocity of wave relative to receiver, receiver is at rest, therefore we can determine, we can detect real velocity 340 divided by velocity of wave relative to source. Source is moving with the v velocity. Therefore, we have to give an opposite velocity to the source. And we have to do same thing for the wave. 340 plus v multiplied by real frequency 22 kilohertz. Apparent frequency should be 20. Then we can simplify it. 340 plus v equals 17 into 2 34, 3 remaining, 17 into 2 34 plus 3 37. V equals, we have to subtract 34 meters per second. Then velocity of car should be 34 meters per second away from the trainer. Answer is 3. A whistling firecracker having a constant whistling frequency is fired vertically upward. It travels initially with an acceleration, then will a deceleration, and finally blast before coming to the rest. An observer at the ground directly below firecracker listens to the whistling sound of firecracker. Consider the following statements regarding the frequency of sound heard by observer. Part A. During the acceleration, it is higher than whistling frequency and decreasing with time. So, the observer and receiver, the source and receiver, gap between source and receiver is increasing. Therefore, we can't hear a higher frequency. B. During the deceleration, it is lower than whistling frequency and listening and increasing with time. Yes, we can consider deceleration is an acceleration in opposite direction. Therefore, we have to consider source is moving towards the receiver with an acceleration. Therefore, it is correct. C. Just before the blast it comes to equal to the whistling frequency. No, they have given before coming to the rest it is blasting. Then only B is true. Answer is true. A sound source emits sound of constant frequency F0. An observer O travels in the direction shown at the speed of 0.1 u, where u is the speed of sound in air. Each of the following gives the correct relationship between F0 and F of the sound heard when the observer is traveling towards the source. We know that the observer is moving directly towards the source. If the observer is moving directly towards the source, F dash should be equals to velocity of wave relative to receiver is u. We have given velocity of sound is u. Velocity of wave relative to receiver. Receiver is moving with 0.1 u speed. Therefore, velocity of wave related to receiver should be 1.1 u. We have to give an opposite velocity to the observer and same velocity for the wave, 0.1 u. Then we can add 1.1 u. Velocity of wave relative to source is at rest, therefore it is u multiplied by real frequency. It is 1.1 u. But now observer is moving in a line like this. Therefore, apparent frequency should be less than this value. It is not moving directly towards the receiver, towards the source. Therefore, f dash should be less than 1.1 f naught, this value, but it should be greater than real frequency. Then we can get second one is the correct answer. An alarm in a car at rest emitting sound wave of frequency 510 Hz. A person on the motorcycle is traveling directly away from the car. What is the velocity of speed? Here, the frequency of alarm at 480 Hz. Speed of sound in air is 340 meters per second. Now I will consider receiver and source. Car is at rest, therefore source is at rest, velocity of wave 340. Receiver is moving away from the car. I will consider velocity as v. Then f dash equals velocity of wave relative to receiver divided by velocity of wave relative to source multiplied by real frequency. When getting velocity of wave relative to receiver, we have to give an opposite velocity to the receiver and we have to do same thing for the wave. 340 minus v divided by velocity of wave relative to source. Source is at rest, therefore we have to substitute real velocity of sound multiplied by real frequency is 510, actual frequency 480. Now we have to simplify it. I will cancel out 0 and 0. Divide by 17, 2, 0. Divide by 17, 3. Divide by 3, 16. 16 into 2, 32, 320. Equals 340 minus v. V should be 20 meters per second. Then we can get third one is the correct answer.